Okay, good morning. I'm working on the LTA here, and I'm on problem number 12. That's on page 2. And I've got my Desmos app open, and I've got the function graphed. And I'm looking for the relative maximum and the relative minimum. So I've got some points here, and it looks like where that point, where that dot is the maximum. So I'm going to say negative 1.3 repeating, 1.185 is a max, and then right at the origin is a min. And when is the function increasing, decreasing, and constant? Well, it's never constant because it's a curve. So I'm going to say it's increasing all the way up to that relative maximum. So from, and I really just care about the x values where it's increasing. So that is going to be from negative infinity to negative 1.3 repeating. And then when is it decreasing? So I kind of like to just go left to right. So it's decreasing from negative 1.3 repeating and then over to 0. And then it starts increasing again. So we'll say at 0 to infinity. So here I want to say even, odd, or neither. So if I'm visually looking at the graph, if this were shifted over and down and it were symmetric about the origin, I could say that it was odd. But since it's shifted over, it is going to be neither. Now, truly the way to be able to tell is by plugging in f of negative x and see if we get back the original function. So I can kind of predict all of my powers are even in this problem. So I'm predicting that I'm going to get back the original function. But if I'm doing a good job showing my work, I'm going to show where I plug that in. So negative x to the 4th, the negatives cancel, negative x squared, the negatives cancel. So in order for a function to be even, f of negative x has to equal f of x, and that's true. So that one's even. So I can see here I've got a third power and a first power. So I'm predicting odd. If a function is going to be odd, we would get back the negative function. So let me just go ahead and make everything the opposite so I can see what I'm going for here. Okay, so that's what I need to happen. Now let me plug in f of negative x cubed minus 4 times negative x. So I end up with negative x cubed plus 4x. So it's a match, so this one is odd. And the last one, I've got odd powers, but then I have this constant that's being added. So that usually means some kind of a shift, which would throw it out of symmetry. So I'm predicting neither, but let me go ahead and plug in and see what I get. Negative 2 times negative x to the 5th plus negative x to the 3rd plus 2. So negative x to the 5th is going to be a negative, so that's going to counteract this positive. So that's the opposite. And this negative x cubed, and that's the opposite, but this plus 2 has no x with it to make it go over to be the opposite. So that's why this one would have to be neither. Alright, so now we're going to find the domain and range of each function. Hint, graph the function. You guys can graph the function. Oh well, I guess we have to find the range. I might need to graph it to be able to see that. This is a cubic, and so and it's shifted 4 to the 4 down. So either way, my cubic normally is right here at 0, so if I go 4 down, that's what it's going to look like. Oh, can't see that. So its domain is negative infinity to infinity. Its range is negative infinity to infinity. Here we have a absolute value which is shifted 3 to the left, 4 down, and it's flipped, and it has a vertical stretch. So 3 to the left, 4 down, and so I don't care so much about the stretch when I'm finding domain and range. My domain is still all reals, so I write it like that. There's no value of x that I can't plug into that and get a solution out, but my range, you can see how by shifting it 4 down here and inverting it, the top of my range is -4, and then it goes down, wait a second, it goes down to -infinity. So I want to write that in the opposite order. So I'm going to go -infinity, and then the top is -4. Here we have an absolute value problem, and if I'm picturing the graph using my transformations, and I'm just talking through these this way just to help you practice with transformations at the same time you're practicing domain and range. You, of course, can use your calculator to graph these while you're doing the LTA, but this is a radical function. It's 3 up, and then it's flipped. So we go, so normally the radical goes like this, but so if we go 3 up and then we flip it, it goes like that. So 3 is going to be the top of the range. The domain, of course, starts at 0 because you can't, actually that's a bracket because it's allowed to be equal to 0. I can pick any positive x that I want. That's for the domain. Now the range, the top of the range is 3, and then it goes down, let's see, it can go down to infinity because I could get a positive value here, but this would change it to be negative. So I'm going to go from -infinity to the top of my range. Okay. Given the graph, describe the intervals where it's increasing, decreasing, and constant. Okay, so on our other graph where we had to do this, we had no constant values, but I can already look right here. Here's my constant. But I'm going to work from left to right, so I'm going to make myself a space, increasing, decreasing, and constant. And then I'm going to move this so you guys can see it. So, oh, do we assume? I think we assume that this goes on forever here. When it's a calculator screen, we can assume that it goes on. So it's increasing from -infinity. So I always start left to right, and I'm always worried just about my x's. And then this is a -2 right here. And then it's decreasing starting at -2. And so I don't, if this is a bracket, I need a parenthesis to start out the next one. And then it stops decreasing at +1. And then it goes back to increasing again. And really this bracket can be in either location, or we could use a parenthesis because maybe at this inflection point it's neither increasing nor decreasing. So we go from 1 to 3 on our increasing, and then we stay constant from 3 to infinity. Okay, so this is 9 minutes. I'm just going to go ahead and keep going. So let's find the coordinates of the local minimum and local maximum of the function. So we want to look at the graph of that, because we're not into factoring that yet. So let me go back and put my function in. So that's going to be x cubed, and then minus 6x plus 8. I think I had zoomed in earlier. So my relative max is going to be at -1 So those aren't numbered by ones. Alright, so negative 1.414, 13.657, and then my minimum is down here at positive 1.414, 2.343. Alright, so name and write the equation for the parent or common function. So here it's f of x equals x squared. Here it's f of x equals radical x. F of x equals x cubed. F of x equals absolute value function. And then describe the transformation. Do not draw a graph. Okay, so we would go, we have a minus 3, so that is to the right 3, and we have a negative on the outside, so that's flip over the x-axis, and then I've got a 1/3 on the outside, so that is a vertical shrink. Here we have a negative that's on the inside of the radical, so that's a flip over the y, and we have a +4, so that's up 4. In number 24, we've got an h of +3, so that's left 3, down 5, and then this 5 on the outside, that is a vertical stretch. And we would probably say like our slope would be that, so we'd go over 1 and up 5. But wait, slope is rise over run. It's still a reciprocal, so I'll have to think about that. In this last one, number 25, we're going to go right 1, up 2. Okay, given f of x and g of x, find the following, then state the domain of the resulting function. So really, when you're doing domains of resulting functions, you kind of just want to look at the domains of the original functions. Okay, so the domain of this one, there's no x you can't plug in, and the domain of this one, there's no x you can't plug in. So in general, you're looking for the union of the two sets. So there are no limitations because we don't have any radicals or anything. So f plus g, we're just going to simply take f, and then we're going to add g. And then we're going to combine like terms. And I like to put it in standard form. So descending order of the variable. And we're done. Now f divided by g, we're going to have to be a little more careful there, because when g becomes a denominator, we have to look at what values of x would make that denominator equal 0. So this is sort of some of your prior knowledge here. You need to factor that out. So I'm not sure how you guys factor, and we're not really doing that till next chapter. But I need two things that multiply to equal 2 that add to equal 3. So that's going to be 1 times 2. So if I put a 1 and a 2 down there, then I've factored it out. So my new domain has to be, I can go from negative infinity up to 1, but I can't equal, oh no, negative 1, because negative 1 is the root that would go in there that would make that 0. Then I can go from negative 1 to negative, oh I see, that'll be negative 2, then negative 2 to negative 1, and then I could go from negative 1 to infinity. So it probably would have helped me to at least have a number line in my mind for that one. So my excluded values were at negative 2 and negative 1. So going from negative infinity to negative 2, then negative 2 to negative 1, then negative 1 to infinity would work. Alright, this is a composition, f of g of x. So I'm going to take G and plug it into F. So x squared plus 3x plus 2, and then plus 1. So that one's not too bad. X squared plus 3x plus 3. Then g of f of x, I'm going to take f and plug it into g. So I'm going to have, let's see, g of f of x equals x plus 1 squared plus 3 times x plus 1 plus 2. So this guy, I need to FOIL it out. X squared plus 2x plus 1. And I need to distribute plus 3x plus 3 plus 2. And now I'm ready to combine like terms. So there's 1x squared, 2x, 3x, there's 5x, 1, 3, 2, so plus 6. And so that's as far as I need to go with that. I don't need to factor it out or anything. And then the domain of that, there's no denominators, there's no radicals, so my domain is not restricted. So here, finding g of f of negative 5, so I'm going to take f, plug it into g, and then I'm going to plug negative 5 into all of that. So x squared plus 4 minus 3, so I took this, plugged it in right there. So let me simplify x squared plus 1. Now I'm going to do f of negative 5, f of g of negative 5 of x squared plus 1. So I'm going to plug in negative 5 squared plus 1, and I get 26. Alright, last page. Alright, last page, and I think I'm going to hopefully make it under the 20-minute mark. So to do an inverse, we're going to switch this to y, and then we're going to flip-flop the locations of x and y. Then I need to get this y by itself. So I think the best way to do that is to square root both sides. I just put it in a different color. So now I've got square root of x equals y minus 4. So if I add 4 to both sides, then y will be by itself. So then I'll have y equals square root of x plus 4. And then I would rewrite that in my inverse notation. Next one, I've got cube root of x minus 6. So I'm going to follow my process. X equals cube root of y minus 6, and I need to solve back for y. So let me isolate this a little bit more by adding 6 to both sides. So x plus 6 equals the cube root of y. Then I want to cube both sides to get y by itself. So that's going to give me y equals x plus 6 cubed. And I could FOIL all of that out, but I don't think that's necessary. So we are just going to switch that into our inverse notation and determine if the function is 1 to 1. So I think the best way for us to do that is to graph it. So 2x minus 6, I'm going to go down to negative 6, go up to, so this is a line, it's a linear function. So I know that any line except for a horizontal line will pass the horizontal line test. So we can say yes, and then this guy, x cubed minus 2x minus 4, I mean I know it's a cubic, so it's going to have this general shape. So it's going to pass the horizontal line test as well, but maybe I could go ahead and graph it. So x cubed minus 2x minus 4, and so, ooh, well I'm glad I did that. So let me show you what the graph looks like. So if you zoom in on this section right here, let's see, the lighting is not great, but you can see there are some spots in this cubic that are going to overlap several times on the horizontal line test. So, good thing I did that. The answer is no.